Hi, I'm Edison. You may have seen me before when I have come here to the Roanoke Public Library. So thanks again to the library for hosting me and coming up with the idea of maybe having me work through some ideas that you could watch and maybe try at home as well. So our plan is over the next several months is to release a few different videos that each present some element of science, some idea, and something that hopefully you will be able to do at home. And so my goals are kind of threefold. One, I want to teach you a little something and then show you a demonstration or two, then show you something you can take away and actually try at home. So today, let's start with, before all of these other things that we might talk about in the future begins, let's talk about where all of these ideas start, and that really is with the atom. So the atom, we know now for the past 100+ years, the idea is that everything that is a thing is made up of atoms. Those atoms are very tiny particles. They're made up of 3 subatomic particles. They're neutrons and protons inside the nucleus, and then we have these electrons zooming around the outside in clouds. So the center of every atom, we say, is the nucleus, made up of those protons and neutrons. And starting about 100 years ago, we started scratching our heads about those little electrons zooming around the outside. You may have seen a model that we call the Bohr model of the atom that has these electrons zooming around the outside. It's almost like a sun with planets going around it. That model is still really helpful for us to understand what's happening. Our more modern understanding is called the quantum mechanical model. Big fancy word. It just means the atom that we think of still works the same, but the electrons around the outside are in these really unique regions of space we can refer to as clouds. So it's not exactly like they orbit the nucleus like we thought perhaps 100+ years ago. Well, within that nucleus you have protons. They're positively charged. You have some neutrons. They don't have any charge at all. And you have electrons. Now those are the little guys zooming around the outside, and those are negatively charged. So one of the things that you may have learned in school was, and may recall, is that if you have a positively charged object and a negatively charged object, they're going to attract to one another. Similar to, and that's not really what's happening here, but it's a good model. And in science, we love to talk about models because they're simple ways of explaining or expressing some really complicated idea. So if you have 2 magnets, one attracts the other, well, positive charges and negative charges are somewhat like that. If I turn these magnets around, if I have a positive charge, let's say, and another positive charge, let's say, and I try to push them together, they're going to repel. So like charges repel, opposite charges attract. Well, this is really important when we're talking about the atom. And for this video and for the next couple, we're really talking about electricity. There are a lot of interesting things that you can do with electricity at home, but I want you to understand what's really happening. So when we talk about electricity, really, we're talking about the movement of, if it's a metal, like in a metal wire, and so inside this wire is a metal wire, it's copper, and so within that, really, we're just talking about the movement of electrons. So if you can remember that, if here is the, let's pretend this is the nucleus of the atom, and you have these electrons zooming around the outside. Well, if you have a whole lot of these atoms, each with electrons zooming around the outside, and I want you to think of the electrons as sort of like the glue between atoms. So if 2 atoms stick together, it really is because of the way their electrons are interacting with one another. So you have one atom here, and they interact because of the electrons. Well, if we're able to cause some of these little electrons to leave an atom and to move to another atom, and we can keep doing that, and we can put pressure on them to do that, and that electrical pressure is called voltage. If we can apply some voltage, we get those electrons to move from atom to atom. That really is what we're talking about when we talk about electricity. So let's take a look at a couple of things that I have here. These are Van de Graaff generators. Van de Graaff generators are kind of neat toys, and really they're just a fancy way of doing this. Have you ever noticed when, especially in the wintertime, when you are running around in the carpet inside with rubber-soled tennis shoes on, and you scuff your feet against that carpet, and you touch something that's metal, and you may get a little bit of a shock. Well, really that shock has to do with electrons that are moving from one place to another. If you have built up a lot of electrical charge and you dump it off onto that metal, then you are giving some electrons or passing along some negative charge to that other object. It can work the other way as well. Well, these Van de Graaff generators are really the same thing. So if you take a look at inside this, there's a big rubber band, kind of like the rubber-soled tennis shoes. And let's move that over. And so sort of like a rubber-soled tennis shoe. Well, there's a roller down here and a roller up here. This is just a hollow globe. Inside is a different roller. So the material that that roller is made of is similar to what would be found on your carpet at home. So when you rub two materials together, then one is going to tend to give electrons to the other. And when that material that has a lot of electrons around it, remember those electrons are all negatively charged, they want to push away from each other. So if we can imagine that this is an electron and this is an electron, and I'm turning the magnet so they repel. So I'll hold them together, but remember those electrons don't want to be around each other. So if they're able to, they're going to push away from each other, right? So if you have two things rubbing together, one gathering electrons from the other, these electrons are going to build up. They don't want to be around each other. So as soon as they have the opportunity, like when you touch something that wants to take the electrons, like metals love to take electrons and give electrons. If you touch something that's metal, those electrons can jump off onto that material. Or you could have electrons from that material jump off onto you if you are lacking electrons. So really, this is just a fancy machine named after a guy, Dr. Van de Graaff, who was a professor a little over 100 years ago, came up with this idea to show how these two things can interact, these two ideas can interact. One thing that donates electrons, another thing that takes electrons, and they kind of stay in place, and they're just looking for a place to go. If this gains electrons, they want to stay here until you give them a place to go. Well, so again, this is an empty globe. This is just a hollow tube with a big rubber band, very similar to the bottoms of your tennis shoes. The roller inside that this is rolling across, it's similar to the roller down here, but it's a different material. The roller up in here is similar to what you'd find in on your carpet or in your carpet. As I start turning this, what's happening is really it's like you running really fast along your carpet. And so electrons are building up, building up, building up, building up, building up on the surface of, in this case, on the surface of your tennis shoes. And once they get up here, those electrons, there's a little metal comb, and it looks like a hairbrush or comb that's inside. It's collecting those electrons and allowing them to go into this sphere. So you can hear the crackling just a little bit, maybe if you listen carefully. You can hear that crackling. What you're hearing is you're hearing the result of some of those electrons jumping through space to get to my finger. And if I let them build up, build up, build up, build up, and then I can reach my hand across, and then hopefully we can hear and see the result of those electrons jumping across. And that crack was, that pop was them jumping, or arcing is a better word. And really that crack and the fact that you see a blue spark is because it's just like lightning. All of the lightning you see on Earth almost always is going to have the same kind of bluish color, give or take, depending on the atmosphere at the time. Same color as these. So what's happening is with the lightning, you're really seeing a lot more of those electrons passing through space. And as they literally go through space, I think of it as they're cooking the air. They're causing those molecules of air, the oxygens and nitrogens that are in the air, they're causing them to literally rip apart, and there's a crack sound that we hear as a result. Every sound comes from some vibration somewhere. So if you have a whole lot of little bitty atoms of air, or molecules of air ripping apart, there's a sudden vibration in the air, and we hear a crack. So that's what really thunder is. Same as what the little crack you heard here. So the electrons, as they arc across or jump across a gap here, it's because something's pushing them. Well, other electrons are pushing them. They don't want to be around each other. You have to force these same like charges together as one pushes apart. Well, if you have enough of them building up, then they are going to push apart. There's a certain amount of pressure they put on each other. Well, if you can get more and more and more and more and more of these charges to build up, then they're going to push more and more and more. So what this really means is that if we get more pressure on those electrons, then we're going to have more what's called voltage. And voltage is nothing more than electric pressure. It's pushing little charged particles, and if you have more push, you have more voltage. Well, there's a certain amount of push over here, so we get enough push to make a spark go across a gap about this big. Over here, this is a little different. This is the same thing as this, it's just bigger rubber band, bigger rollers, the material's more, the sphere is larger, and I do have this hooked up to a motor, and that motor is going to turn this faster than I can really turn it with one of these, which means instead of a little bit of pressure, there's a lot of pressure, which means instead of a little bit of arc or a little bit of a gap that those electrons can jump across, we're going to make that gap even bigger because the voltage is greater. So for that, maybe with the humidity in the room, etc., maybe we're talking 5,000 to 10,000, maybe 30,000 volts. Earlier, we saw some of that. Here, that might be different. If we get really lucky, we'll find out. And I'll estimate how much voltage or how much electric pressure is going. Now, the humming you hear is just the motor. And so as we turn this, we'll get that going. And you hear some crackling. My hair, I can feel tingling, so it's building up So the hair, I can feel what little hair I have. It's being attracted. And you can hear some crackling. And that crackling is partly because in the way I have these rollers arranged, we're pushing electric charge. We're pushing negative charge. So I'm letting it build up, build up, build up. So let's give it a place, that electric pressure, we're going to give it a place to go. So let's see if it wants to come to me. And I felt that one. So yeah, so we're looking at probably, my guess is somewhere around over 100,000 volts. It's well over. And you can estimate by the distance that these jump. Let me turn that off, and there's still that charge that's built up in the air. You know, if you have a bad hair day in the wintertime, it's really because of this. You have a lot of electric charge built up, and it causes your hair they all become charged similar to one another. So if one hair is negative and the other hair is negative because it's picking those negative charges up from the surroundings, then they all want to move away from each other. And so your hair starts to kind of get frizzy a little bit. So you have a bad hair day. That's really what's happening. So there's some places in the world where you will never have a bad hair day. It all depends on the static that's available around us. All right, so let's take a look at some things you can do at home, and these same ideas are applying. So this is something you can try at home, and not just try, but actually do a pretty good job at. If you will take a piece of PVC pipe, same stuff you get from a building supply store. There might be some in your garage or maybe even your backyard right now. So you can get any length. Longer lengths and larger diameter lengths tend to work a little bit better. You want a good surface area, but something like this would work really well. And remember that these big rubber bands, similar to your shoes on the Van de Graaff generators, and the rollers inside that are similar to your carpet at home. The reason why electrons jump from one place to another is because those materials are very different. And you could look up on the internet what's called a triboelectric, Triboelectric, triboelectric series. And you're going to be able to find this with a good Google search. And you'll have a whole list of different materials. And if you pick something at the top end and something at the bottom end, rub them together, you're going to get a transfer of electrons from one material to the other, and you are going to have the same effect happen. You might even hear some crackling happen. So there are a lot of different materials on this series. So look that up. One of the things that works really well is at one end of that series is PVC pipe. At the other end happens to be hair, human hair, or in this case rabbit fur. Wool will work. If you have a cat at home that is really cooperative with you, there might be two on Earth. You could take this and actually rub it carefully along the rabbit's fur, or the cat's fur, and it will have a similar effect. Got to tell you, cat hair works better than rabbit for whatever reason. All right, so I'm going to take this and rub it together just like the Van de Graaff generator does when it was acting, and just like when you are when you're rubbing or running across carpet with a rubber-soled tennis shoe. You're rubbing these two different materials together, and if I get this close to the microphone, you can hear a little bit of crackling. Tiny bit. A little bit of crackling you can hear. That crackling is a transfer of electrons. You are actually hearing large groups of electrons being transferred over. So I'm building up static charge, building up static charge, building up negative charge. And turns out that water is what we call polar. There's a slightly negative end to the water molecules, and because it's H2O, the oxygens become slightly negative, and the hydrogens become slightly positive, which means it's sort of like they're really weak magnets. But when they get close together, they stick together really well. We call it cohesion, and that's what causes a water droplet. If you drop a little bit of water on the table and it stays in a drop, cohesion holds those water molecules together, and so that's why we see water kind of hold the shape it does in a drop on a table. Well, if I take some soapy water, I have soapy water on this, and you can do this at home as well. I'm going to blow a bubble in that soapy water. And we'll see if we can do this without it popping. It's going to pop. But right now, that soapy water, those little molecules of water, are somewhat like magnets. There's a negative end and a positive end. If I make this electrically charged, then it's going to attract the opposite charges in that water. You hear the crackling. So I know this is charged up. Now watch, now watch, now watch. You can already see the bubble moving. So it's moving toward this charged PVC pipe. You can watch it move backwards this way. And if I get a little closer, it'll move even faster. And it actually pulled up until it popped on the edge of this. Let's try this one more time and see how high I can get it. And this got a little bit wet. One thing that static does not like is moisture. So on really humid days, static electricity doesn't build up too much. It likes the drier days and cooler days. So you can hear the crackling. So we're building up charge, building up charge, building up charge. Let's see if we can actually get that water. You can see the bubble moving. Let's put it directly over and see. You can watch the bubble moving up, there it goes. And we can move those bubbles whichever way we want because of the attraction between the negatively charged PVC pipe and the bubbles themselves. All right, so you could try that, and you could imagine that it's because of the water molecules, it's attracting those water molecules. Well, you could also try doing the same thing, turning the water on in your sink, letting the water run very slowly, putting this next to it when it's charged up, and you should see the water that's dropping, you should see it moving toward the PVC pipe. Let's try one more thing that also is just as easy to do. I have some empty aluminum cans. Well, aluminum cans are metal, and let's try this, and I have another one. Let's try that. Now let's charge up this PVC pipe again, and we'll make this negatively charged. Well, those cans right now, they have no electrical charge, net electrical charge, so they're neutral. But metals are really good at letting their electrons move around when you make them. I'm going to, as I put these close, as I get them closer and closer and closer, this is negatively charged, that's neutral, but the electrons inside can move around pretty freely. And as I get this closer, it's pushing the electrons away, leaving this side a little bit positive, which means we can get it closer and closer and closer, and then cause these to move. So what's happening is those electrons are free to move. The protons in the center of the atom are not free to move in a solid. But the electrons, remember, those can move from atom to atom pretty well. So the can is being attracted because this is negative. As I get it close, it's pushing the negative charge carriers, the electrons, away, leaving this side positive, and opposites attract. And so this will work with both cans. And the charge lasts for a long time until one way to get rid of that charge is just to let your hand run along it a little bit. Same thing for, if you've ever noticed, for staticky hair. If your hair is really staticky, your hands may be a little bit damp or a little bit moist or even dry, pat your hair a little bit and the static goes away. A lot of the static goes away. So let's try one more thing. I do have, and this is something you can try at home too, is this, all this is Mylar. Mylar is the stuff they make the silver party balloons out of. If you get one of those, they also sell it as a survival blanket at Walmart. For $3 or $4, you get the survival blanket. It looks like a foil blanket. Unroll it, clip it into little streamers, and you can take that, and this also works really well if you charge up your new electrical magic wand. You're making it negative, making it negative, making it negative. That Mylar is coated with metal. Remember, metal loves to allow its electrons to move around. So I'm making this negative. It's going to repel other negative things and attract positive things. So this is neutral. I'm going to give it some negatives. So the negative particles, electrons have moved to the other end, leaving this end positive. So it's attracting. So if I shake it apart, let's charge it up a little bit more. So if we get enough of a charge built up, there we go. So we're able to repel because this becomes negatively charged. As soon as it touched this, it gained some negative charge. And now we're able to, a little more, there we go. And so if you are a Harry Potter fan, and you're disappointed that you can't levitate things, well, Hollywood only can do it on camera. But if you're careful, you can do it in real life. So give that a try and have fun.